Right, ladies and gentlemen, we have one more speaker prior to lunch, and of course, this presentation would be for AI meets HPC in scientific computing using Graphcore's IPUs. And presenting this is Senior Regional Vice President of EMEAI and Asia Pacific Sales at Graphcore. Please welcome Mr. Fabrice Moizan.
Hello, everyone. My name is Fabrice Moizan. I'm Senior Vice President Sales at Graphcore. Today, I will be giving an introduction to Graphcore and to our machine intelligence compute systems. And I will show you how we are enabling huge advances in machine learning, AI, and HPC. Our initial goal at Graphcore was to build the best processors and software tools for the next generation of AI. And I think this is really important. We need to get across the idea that we're not building a cheaper GPU. We're not trying to build a better GPU. We are building a new kind of processor that's going to allow people to create the next breakthrough in AI. So, a very quick introduction. Here is a little about Graphcore. Put simply, Graphcore develops processors specially designed for AI and machine learning workloads. We provide hardware technology as the IPU processor and software as the popular software and development tools, as part of a complete solution to enable innovators to solve current and future machine learning problems. So, moving on to the technology and really trying to describe where we're different and why we would win. I think the key thing to get across is that AI is not some static thing. It's growing and evolving very, very quickly. The requirements are changing very, very fast. And what we've built is something that anticipates where this whole evolution is going. We started by looking at supervised learning, and we've gone to an unsupervised learning with transformer-based models. The challenge there is that the models are getting really, really big. The data sets to train them are getting really, really big. And the compute, as a result, is the multiple of those two. And therefore, the amount of compute required is going up on an exponential basis. That is clearly unsustainable. And we need to build more complex models to be able to overcome that challenge. We need to be able to look at the data that's coming in and steer it to the parts of the model where it's relevant, where it gets to the compute. Rather than just computing on large blocks, we need to be able to break that down and compute on a sparse basis, recognizing the complexity in the data structure. And to be able to do that, you need a processor that is able to operate on a much more fine-grained basis with many more parallel compute paths and much more complexity described in the data. That's what the IPU has been designed to support. We also need to get across the idea that we can do what is being built today and running on GPUs. In many cases, we can be faster than CPU and a GPU with our ML perf results show. But where we're really going to win is in next generation of AI models, where we need to show people how we can support that. So now let's consider the processors that are predominantly being used for machine learning today. Let's have a look at those. We're familiar with CPUs. They were developed for scalar processing and running general purpose applications. The GPU was designed for graphics or vector processing, and in some cases have had some additional cores to help address some of the workloads specific to machine learning. But essentially, these are processors that were designed for different purposes. Graphcore, we've been able to work with many of the leading innovators in machine intelligence. They've told us that today's CPUs and GPUs are holding them back. What they need is a new type of processor that can efficiently support much more complex knowledge models. And this is why we've created the Intelligent Processing Unit, the IPU. The IPU is built from the ground up to meet these innovators' needs and to help them make new breakthroughs in machine intelligence. This is our processor. It contains 60 billion transistors, and it's been developed at TSMC. It also supports an impressive 250 teraflops of AI compute. This processor has approximately a total of 1,472 dies, which means it has 8,832 independent processor threads. It also contains a massive amount of in-processor memory of 900 megabytes. That means almost 1 gigabyte of SRAM memory available on each IPU processor. This makes data available at super-fast bandwidth processor cores to memory for 45 terabytes per second. It supports the high-speed IPU links connectivity to enable connectivity between IPUs so that multi-IPU scale-out can be achieved and seamlessly managed by the Poplar software. And finally, it is as efficient for training models as for production. All these new innovations have come together in a single breakthrough product, the M2000. Unlike GPUs, which need a server plus expensive InfiniBand networking cards, the M2000 can be easily added into an existing converged infrastructure data center with the dedicated AI-focused IPU Fabric networking included inside the box. The M2000 IPU machines features a 4-cylinder IPU engine with 4 of the Mark II IPU processors, combined with an advanced airflow cooling system to fit in an easy-to-handle 1U chassis. The IPU engine is combined with an IPU Fabric chip, allowing multiple M2000s to be added into the rack and racks of M2000s to be connected together to build large IPU-PODs. And finally, all of this is supported with our in-processor and streaming memory. Our IPU machine, the M2000, is our building block for scalable IPU machine intelligence systems. Up to 16 of these M2000s can be stacked in an industry-standard rack into an IPU-POD 64. This provides the core building block for further scale-out into the exascale domain, allowing potentially up to 64,000 IPUs to be supported. This will allow customers to start small and then seamlessly scale to thousands of IPUs in order to tackle huge workloads in the multi-trillion parameter model area, while allowing independent scaling of CPUs, IPUs, networking, and storage resources. The Poplar SDK provides the complete software stack which implements our graph toolchain. Poplar allows innovators to use existing high-level machine learning frameworks such as TensorFlow, ONNX, and PyTorch, so that you can easily target your existing models to the IPU, even if they were originally developed for CPU or GPU. This enables maximum portability and ease of use for out-of-the-box performance. However, for those who are wanting to squeeze maximum performance out of the IPU, it is possible to use Poplar to develop models at a much lower level, much closer to the hardware. To complement the Poplar software, we have comprehensive virtualization and workload manager support, with support for standard workload managers like Slurm or orchestration systems like Kubernetes or OpenStack, and with OpenBMC management built in, we can integrate into any data center converged infrastructure management system and interface to system monitoring such as Grafana. And with the developer community pieces that we've been developing, I think that this all goes towards the maturity of our popular software. This ecosystem has been building out rapidly and we continue to expand. As an example, you can look at what we've been adding very recently in our model garden. For instance, around speech models, language models like GPT and Vision Transformer. We are really accelerating the numbers of models that we can support with the system and the developer environment. For Graphcore, making the system cloud native is very important. Today we have Slurm operating, we have Kubernetes operating, and more is coming. So now let me talk briefly how Graphcore performs against competitive solutions. Here is a good example demonstrating that Graphcore IPUs can bring performance, TCO, and power benefits. In the latest MLPerf results published in December, Graphcore was able to present some outstanding performance results against competitive solutions. In this particular example, for an equivalent hardware platform, we were able to train BERT large model 8 times faster than Intel Habana and 2 times faster than the DGX A100 from NVIDIA. As the AI models are getting larger and larger, the innovative hardware architecture and system scalability offered by Graphcore IPUs is a game changer. I presented earlier Graphcore scalable hardware platforms. All the support for this in terms of scale-up and scale-out has been built into our Poplar software. So we have solutions in Poplar that support scale-out and the communication libraries that help us to communicate and build very large models across IPUs in order to support model scaling as well into large models. It has been a big theme over the last couple of years. More and more, we're seeing a fast-growing trend from HPC towards AI. This has been driven by the availability of larger amount of data and the need for more accurate information. The future is really about accelerating HPC workloads into AI, or simply the existence of new kinds of machine learning models used into HPC use cases. To make this approach successful, we need new types of systems. This hybridization of HPC and AI is happening today, and we see that single monolithic systems are not able to satisfy both worlds, HPC and machine learning. For typical HPC workloads, we have systems based on hundreds of thousands of CPUs and GPUs. We can consider them also as hybrid systems in some way. For AI workloads, we can easily use pod systems able to scale to hundreds of racks and thousands of IPUs or GPUs. But for new heterogeneous types of workloads, it will require new hybrid systems complying with the benefits from both worlds. And this is the new way we will be able to accelerate and achieve sustained exascale performance. Our IPU architecture was specifically developed for AI type of workloads and doesn't fit typically with HPC applications in the pure form. Nevertheless, IPU can improve and extend the HPC classic simulation via surrogate calculation models. If we replace the classical simulation solvers using ML models, we can achieve great results. This approach uses the data generated during HPC simulations to train the ML replacement model, which then predicts responses for new iterations of experiments much faster. Let's take an example from a CFD, computational fluid dynamics use case. In data generation phase, we use classical HPC solvers to generate data. Then we use generated data to build the model and train it. When the new iteration will come, we will use our trained model to predict the results. If we look on the diagram at the bottom of the slide, we can see that simulation time can be reduced significantly. Modeling experiment phase will stay in both scenarios, but simulation time can be accelerated by the implemented AI module. As a conclusion, many researchers already use such a process, and in many areas, the integration of the AI acceleration module with HPC simulation brings great results. HPC is an essential tool fueling the advance of computational science. Now, AI is increasingly being used alongside more traditional HPC techniques to run large-scale simulations in an accelerated time frame. With AI, researchers can make scientific advancements more quickly across a wide range of fields, from weather forecasting and protein folding to computational fluid dynamics, cosmology, and high-energy physics. IPU-based systems from Graphcore are the ideal solution for AI workloads in these areas of scientific research. The European Centre for Medium-Range Weather Forecasting, ECMWF, has developed a number of deep learning models as part of a publication investigating the use of machine learning in numerical weather forecasting. Graphcore engineers took one of ECMWF's publicly available forecasting models, a multi-layer perception MLP model, and ran it into our IPU with dramatic results, obtaining a 5x speed-up chip for chip in training throughput over the leading GPU without optimization or modification to the model or any hyperparameters, and with only a handful of minor modification to the code. In ECMWF's original paper, they stated that their machine learning-based emulators performed 10 times faster on GPU's hardware compared to their existing scheme in a CPU. On that basis, IPUs would be a massive 50 times faster than ECMWF's existing simulation methods running on a CPU. This is just the beginning of our journey. We are currently working with partners such as Atos to validate more practical examples and use cases where the IPU can accelerate HPC loads. We also work with scientific institutions such as the RAISE or GENSI consortium to expand the portfolio of models to enable them to operate on the IPU. The areas we work on with our partners include AI for turbulent boundary layers, AI for wind farm layout optimization, AI for data-driven models in reacting flows, smart models for next-generation aircraft engine design, AI for wetting hydrodynamics. To hear more about our solution, I invite you to the speech of Professor Pavel Gebner, Convergence of Machine Learning and High-Performance Computing Systems for Empowering Classical HPC Workloads, and our speech together with our partner Atos AI at supercomputing scale. I would like to thank you for listening to my presentation today. I wish that was helpful and you learn more about IPUs and how we're trying to tackle the HPC to AI revolution. Thank you very much for your time.